Okay, today we are doing Unit 3, Day 5, which is going to be on rational expressions. So a rational expression we defined up here as being any type of expression where you have a polynomial both on the top and on the bottom. So one of the qualifications of a polynomial was that you didn't have any negative exponents attached to a variable or any variables in your denominator. And if you have that, it diverts and is no longer a polynomial. It's now a rational expression. So before we get into rationals themselves, I need you to kind of really understand our canceling rules. We've talked about this here, how you can cancel factors, but you can't cancel terms. So the first example up here, thinking back to the past, is that when you have 2x and x squared, x is a factor, and so are x squares, because you have things that are just being multiplied together. So this would be like having 2 times x and x times x. And since everything's being multiplied together, each of these both have x as a factor, and therefore we can cancel one of them out, and our remaining solution would be 2x. Okay, what I mean by terms, think how funny it would be if I took 66 divided by 63, and I made it 60 plus 6, and 60 plus 3. And then I canceled those 60s out, because they were the same, right? And then I gave myself 6 divided by 3 and I said 2. In what world is 66 divided by 63 2? It just doesn't work. The problem here is that these 60s are terms and they're not factors. If we wanted to look at this factor idea, we could say, well, this is 3 times 22. And we could say that this is 3 times 21. Now each of these are factors instead of terms. And we could cancel out a factor of 3 for dividing. And my solution would be 22 over 21. That is an algebraically sound way to look at these problems. So to do that, in examples 3 through 6 here, you have a couple rational expressions. This is something you should get used to seeing. This is a rational expression in standard form. But the problem is everything's terms, so I can't cancel out these terms just like I couldn't cancel out my 60s. So what we're going to want to do is we're going to want to factor. This is a rational expression in semi-factored form. We can go a step further here, so let's do that. Y plus 7 divided by y plus 7. This is y plus 3, y minus 3. You can see why our factoring needed to be refreshed a little bit. So now I'm looking at these, and I'm seeing that they share a common factor, and that factor can be canceled out. So my solution here would be 3y. I'm actually going to put this back in that factored form that we had. This would be my solution. So you want to factor out, cross out any factors that they have in common both in the numerator and the denominator. Something else here though says identify any values for which the expression would be undefined, because now we're dealing with there being variables in our denominator. And the issue with that is a variable can be any number. And in this case, it can be any number except a few numbers, because there's certain ones that are going to make this 0. For instance, if I put a 3 in here, 3 squared would be 9. 9 minus 9 would be 0, making this whole expression here undefined. So we don't want that. So when the bottom is in factored form, you want to take each of those values and say, well, what would make them, we don't want that equal to 0. So y can't be negative 7. If y plus 3 is in our denominator, and we don't want it to equal 0, then y can't be equal to negative 3. And then we have one more, y minus 3. We don't want that to be 0, because we don't want this to be undefined. So we can say y can't be equal to positive 3. So when every time you're simplifying, when we're multiplying, dividing, adding, or subtracting our rationals, we have to add that added step of listing all the values for which the function would be undefined. So this is the same as 3y over y squared minus 9, except that y cannot be 3, negative 3, or 0. All right, let's go through that process again. Step 1 is going to be to factor. We're going to do p plus 3 and p minus 1. On the bottom, this factors to p plus 5, minus 5, plus 3. Now, I just wanted you to get in the habit of, before you cancel, saying what p can't be equal to. In this case, it can't be equal to positive 5 or -3, both of which would make the expression undefined. Now you can cancel what needs to be canceled. And I'm left with p minus 1 over p minus 5. So my solution simplifies down to p minus 1, p minus 5, but you still want to state your excluded values, those numbers in which can't be put in there. So just a note on this, you do include the -3, all right, even though that's canceling out, it's still going to show us something. So I'm not sure if you know your parent functions yet or not, but a rational function looks something like this drawing that I have up here. So when we're saying that p can't be equal to these things, values, this is what's going on here. I have something called an asymptote here at 5, so it's literally a break in the graph. There is no point along either one of these lines where p is going to be equal to 5. And then also at 3, I have a graph that goes through that point, but there's a little hole here. So we'll get into the holes and the asymptotes and all the other aspects of how this graph works on a later date. But I just want you to know that that's what it means. If p can't equal that, when we go to graph it, it's not going to be there. Skipping ahead a little bit, I want us to go down to problem 7. You'll try some of those other ones on your own. I want to talk about multiplying our rationals, and I want to actually start with these kind of monomial terms. So notice there's no factoring that needs to be done here. When you are simplifying, we're just going to assume that no variable equals 0. So technically we should sit here and say y can't be equal to 0 and x can't be equal to 0. When we're dealing with these monomial ones, usually the instructions are going to say that it's implied that they're not 0. Now, you can pretty much assume there's a bar that goes across this whole place, because multiplication, you just multiply across the top and you multiply across the bottom. You should have seen that in your warm-up today with your fractions. So for this, I'm going to cancel as much as I can without actually ever having to multiply this 21 and this 16. 8 and 16 is 2, 7 and 21 is 3. I have 2 y's up top, and I have 3 down below, so that's going to leave me with 1. And I have 1x, so that's going to leave me with 2 x's. So looking at everything that I have left here, it looks like I had nothing left on top, and I had 3 times 2, which is 6 y x squared, or x squared y is probably the better way to write that. So that's all I would have left there. So we're going to apply this principle of canceling and multiplying across the top and multiplying across the bottom when we do a more general rational expression multiplication problem next. So I'm going to have you jump to problem number 10. All right, so when we have polynomials on top and the bottoms, things that can be factored, you want to factor first. So that's the first step I'm going to show you. And I picked this particular problem because I know that we haven't necessarily seen something like 1 minus k squared yet. Or if we have 1 minus k squared, that's still going to be 1 minus k, 1 plus k. But I'm seeing here at k plus 1, what's the relationship between 1 plus k and k plus 1? So my advice to you, and there's no wrong way to do this, but my advice to you is anytime you want to switch the order, think about 1 minus k squared is the same thing as negative k squared plus 1. So if I want to change that, I can make it negative k squared minus 1 and pull that out. And I think you might find that helpful. So I'm going to rewrite this as k minus 3 over k plus 1 divided by a negative. I'm pulling it out in front. This top is going to factor to k minus 3, k minus 1. And this bottom is now, k squared minus 1 because I pulled out the negative, k plus 1, k minus 1. All right, so this is really a great problem because now we have some other things. So not only did we do this creative factoring here, but this is a division problem this time. So division, just as you did with your regular fractions, you just flip the problem. And when I do that, I get k minus 3, make that look like a k, over k plus 1 times a negative k plus 1, k minus 1, k minus 3, k minus 1. So if we want to look at this as multiplication without canceling anything first, just to kind of show you the long way to do it, all nice and drawn out, this would look like one rational expression with a negative out in front. I'd have a k minus 3 factor on top, a k plus 1, and a k minus 1. And on the bottom, I'll have a k plus 1, a k minus 3, and a k minus 1. Okay, so that's kind of what you can do. If you want to cancel in this step, that's totally fine as well. But now we can see that everything's going to cancel out with everything, and this whole problem boils down to a -1. Okay, so this is great. You're not always going to get just like a constant as your graph. This one just really worked out that way. But I still want to make sure that you're listing the values for which it's undefined. So now we have to list everything that k can't be. So that is anything that is in the denominator once you do your multiplication, or anything that ever was. So we kind of have to do it in this step. So k can't equal -1 then. This would be another -1, and this would be another +1. And then we want to do it in the last step as well. So checking here. I already listed -1. I need to list my 3, and then I already listed my 1. So there's 3 values in which k can't be for this specific problem. Okay, so we have multiplication, we have division, we have our monomial looking rationals, and we have our polynomial looking rationals, and you'll try these others as well, the answers to which all of these solutions written out are in Canvas, obviously. The next section here is simplifying complex fractions. You're going to do that on your own, and then again, just make sure you check your answers. So once you look at a complex fraction and the whole process to that, we're going to use that when we're simplifying complex rational expressions. So I have one more example picked out for you. And that's going to be example number 13 here. So as far as excluded value goes, remember anything that was ever in the denominator, any factors involving a variable, you want to list under your like can't be equal to. So here I have x squared minus 9 over 4 and x minus 3 over 8. This is just kind of like a big division symbol here. So we can rewrite it as a division problem if we chose. I could rewrite that as x squared minus 9 divided by 4 divided by x minus 3 over 8. But division with fractions is nothing more than multiplying by the reciprocal. So that's going to be x squared minus 9 over 4 times 8 over x minus 3. Okay, so I'm getting my first factor that's in the denominator, so I'm just going to make a list here. X cannot be equal to 3. In order to do this, we're going to factor. So this is x plus 3, x minus 3, and 8. And down the bottom, I have a 4 and an x minus 3. These two factors, not terms, but these two factors can cancel because it's in both the top and the bottom. And now I have an 8 and a 4, and that can be simplified as well to a 2 and a 1. So my solution here is 2 times x plus 3. You can leave your solution like this. This would be considered a polynomial in factored form where everything's pulled out. Or you can multiply or distribute back in, and you can leave it in standard form. I'm not going to be picky between the two, and you might find that my solutions have a nice mixture of both problems as well. So go through the rest of this worksheet, apply all these concepts that we've just gone over. If you have any questions, you can totally ask me. Just come find me. And then you have your little exit ticket in there that you're going to do, which is just kind of conceptual. It's going to walk someone through the steps of a problem. And then, of course, you have the Unit 3, Day 5.